In our final video on quantum orbital theory, we're going to focus entirely on quantum numbers. Quantum numbers are, again, the four different numbers that are used to describe an electron's energy level, subshell, orbital location, and spin direction. And these four quantum numbers are used for each individual electron that is owned by an element, meaning that every single electron that belongs to one element is going to have what we call a four-digit quantum number address, where each of the four numbers represents the four different aspects that we have talked about so far. The first number, the principal quantum number n, is the energy level, which represents how far the electron is away from the nucleus. The second quantum number, our angular momentum quantum number, represented by L, is the subshell quantum number, which represents the type of 3D space where the electron is located. The relationship that L has with n is that L can be any integer as long as it is not bigger than n minus 1. So, for example, if L is equal to 0, that tells us that we are dealing with an S subshell. If L is equal to 1, that tells us that it's a P subshell. If L equals 2, that tells us we have a D subshell. And if L equals 3, that is an F subshell. There are more subshells that are technically possible with higher L values, but we do not see them in elements that exist on Earth. The next quantum number, our magnetic quantum number, is our orbital quantum number. And our orbital, which orbital an electron is located in, depends on what type of subshell, which is why the orbital value, m sub L, depends on what our L value is. So m sub L can be any integer as long as it is between negative L and positive L. So if we look at P subshells, for example, P has an L value of 1, meaning that in the case of P orbitals, let's draw an orbital energy diagram of P orbitals here. That means that our orbital number, m sub L, can either be positive 1, 0, or negative 1, because it is any integer between positive L and negative L. And these numbers here correspond in numerical order with each of the orbitals of the subshell. So this would be m sub L equals negative 1, the first P orbital. This would be m sub L equals 0, and the last one would be m sub L equals positive 1. Our final quantum number, which is actually the easiest to understand, is of course our spin number, or the spin direction, where if the electron has a top spin with its magnetic field pointing up, that corresponds to a spin number of positive 1/2, and conversely, with a backspin where the magnetic field is pointing downward, that corresponds to a spin number of negative 1/2. These numbers become easier to understand once we actually look at applying them to an individual element's electrons. So we start with the easiest element to analyze, helium, where it only has one subshell with 2 electrons in it. So we know, but simply because helium is 1s2, we know its energy level and its subshell quantum numbers. So n equals 1 because helium's orbital is at the energy level 1. We know that this is an S subshell, which means that L has to equal 0. And because this only has one orbital, and because we know that m sub L, our orbital quantum number, has to be between positive and negative L, m sub L also has to equal 0 because there is only one orbital in an S subshell, and helium has 2 electrons, meaning that its spin quantum number can either be positive 1/2 if the electron's magnetic field is pointing up, or negative 1/2 if the electron's magnetic field is pointing down. And again, most importantly, 2 electrons, each electron has to have the opposite spin direction, because it's impossible for 2 electrons to move in the same direction. They must be moving opposite to one another. However, as soon as we start dealing with p subshells and above, quantum numbers get a little more complicated, so we'll take this a little bit slowly. Everyone make a correction. This element that we're looking at is oxygen. We are looking at oxygen's valence shell here. You know that that's the case because if we write this in core notation, helium are the core electrons. This would be oxygen's, my mistake, 2s subshell, and this would be the 2p subshell. So this would be helium 2s2, 2p4, and we know oxygen has 6 valence electrons, so we know what we're looking at. So here, if we wanted to analyze every electron, there's quite a few variables that we could look at here. So in oxygen's case, because its core electrons are at energy level 1, N can either be 1 or 2 because its electrons occupy energy level 1 or energy level 2. Now, we see for the first time that oxygen has a p subshell, meaning that L can either be 0 if we're dealing with oxygen's s subshells, or it can be 1 if we're dealing with p subshells. So again, L equals 0 corresponds to an s subshell, and L equals 1 corresponds to a p subshell. We know that our orbital number, our magnetic quantum number, can only be 0 if it corresponds to an s subshell. However, as we saw earlier, again, m sub L can be any number between, or any integer between positive L and negative L. So each of oxygen's p orbitals would be given the magnetic quantum number m sub L is either -1, 0, or +1. So in the p subshell, m sub L can be -1, 0, or +1. And again, with m sub s, it's exactly the same as before. Electrons can either have a spin number of +1/2 if they have a top spin, or -1/2 if they have a backspin. Now, if we wanted to address the specific quantum numbers of a specific electron, let's look at this electron here. So we know this electron is at energy level 2 because it's in the 2p subshell, so N is equal to 2. And we know that this is a p subshell. P means that L is equal to 1, so there's our angular momentum quantum number. We know that this electron is in the second orbital of the p subshell, and because we write the magnetic quantum numbers in numerical order, counting upward, we know that this orbital has a number 0, and when we look at the spin direction, we see that the spin direction is pointing up, which means that its spin number is +1/2. Now, we can take a look at these in a more complicated example, arsenic. Let's quickly double check exactly what arsenic is supposed to look like to know what we're looking at here. So here is arsenic, which means that its core electrons we can represent using argon in noble gas form, which means if we write this in core notation, this would be argon 4s2, 3d10, 4p3. Again, 4s2, 3d10, 4p3. Now, again, if we are to break this down, again, argon's N number, its principal quantum number, can go as low as 1 for the bottom electrons and as high as energy level 4. So again, N can be any number between 1 and 4, corresponding to energy levels 1 and 4. We see for the first time in our examples, the example of a D subshell where L is equal to 2. So because argon can have S, P, or D subshells, that means that its L value can be 0 for S subshells, 1 for P subshells, and 2 for D subshells. Now, if we analyze what the orbital quantum number, what the magnetic quantum numbers can be in a D subshell, remember that M sub L can be any integer between -L and +L. We know for a D subshell that L equals 2. So if we write all of our integers from -2 to +2, we get -2, -1, 0, +1, and +2, and those are our corresponding magnetic quantum numbers. Each one of these represents one of the orbitals that is possible in a d subshell. And again, spin direction, easiest one to understand, magnetic field points up or magnetic field points down. So if we were to take one example of an electron, let's take this one here in arsenic's d subshell. So because this subshell is 3D, it's energy level 3. There's our principal quantum number. It's a d subshell, so that means the L value is equal to 2. M sub L is the orbital number, so if we count up, this is -2, -1, 0, +1, +2. This is in the last possible orbital of the d subshell, and because this electron is oriented downward, we give it the spin quantum number of -1/2. That concludes the quantum orbital theory series of lectures. At this point, because in my experience, writing the quantum numbers independently of writing orbital energy diagrams, electron configurations, and orbital drawings, traditionally students find this to be the most tricky. So for now, you can try the ample number of practice problems that have been listed after. Stay tuned in the next series of videos where we will be analyzing molecular structure.